Assalamu alaikum students. This is your teacher Muhammad Umar Khattak for the subject project management. This is our 27th lecture and chapter number 8. And today we'll be discussing how to construct AON and AOA networks, that is activity on node and activity on arrow networks, and Gantt charts. Constructing AON network, activity on node. The action plan contains the information we need. It is a list of all activities that must be undertaken in order to complete a specified task. The time each activity is expected to take, any non-routine resources that will be used by the activity, and the predecessor activity for each activity. For example, we might have an action plan like that shown in the next slide. We have a sample of an action plan, an example, a simple one with 6 activities, tasks which are known as A, B, C, D, E, F, and their predecessors are shown as activity A does not have any predecessor, activity B does not have any predecessor, activity C has activity A as predecessor, and activity D has activity B as predecessor. Now we have to construct activity on node network from this action plan. Now, let's construct the activity on node network from the action plan that we just studied in the previous slide. We begin with this node called start, and activities A and activities B have no predecessor. So we draw arrows out of the start to each of them. The arrowheads only show the direction of the precedence. Activity C follows A, activity D follows B, and activity E follows B. Now, activity F follows both C and D. The action plan does not indicate any further activity is required to complete the task. So we have reached the end of this particular plan. So we draw arrows from activity E and F to the node called end. Many of the project management software packages will generate these networks on request. Construction of activity on arrow network. Again, we begin with the node called start. Activities A and B have no predecessor, so we draw arrows labeled A and B from start and terminating in circle-shaped nodes number 1 and 2 for easy identification. Activity C follows A, activity D follows B, and activity E also follows B. Let's add these arrows to our AON network, labeling the arrows and nodes sequentially as we go. Note that activity F must follow both C and D, but any given activity must have its source in one and only one mode. Therefore, C and D must terminate at the same time, at the same node. Erase activity D and its node, and it is now clear that the handwritten network should be drawn in pencil and redraw D to end at the same node that terminates C. We now add activity E following B and F following C and D. Because E and F have no successors, they will terminate at the end node. Again, we look at the same action plan that we looked at before, where we have activities from A to F, with A and B having no predecessors activity, and activity C having activity A as predecessor, while activity D follows B and E follows B, while activity F can only be completed once C and D have been completed. Now let's try and construct the activity on arrow network. First that we need to do is draw a node which is going to start the proceedings. This is going to be called 1. Then as we have to denote all the activities on the arrows, so we draw the first activity arrow from that node, and we call it as activity A. Now, activity A finishes up into another node, which would be an event, and this would be called S2. Now, previously we would write on the nodes all the activities names. Right now, this is activity on arrow network where we have to write names of the activities on the arrows. Now, activity B also starts without any predecessors. So we started from the 1 node and then finish it up with another node called 3. Now, activity C follows activity A. So we started from the second node, and then you draw an arrow and finish up with a node 4. Now, we know that activity D follows activity B. And as both activity D and C are prerequisites for activity F, so we make them finish up at the same node called node number 4. Activity E has activity B as predecessor, but it does not have any successor activities, so it ends up in a finishing node called node 5. Again, activity F does not have any successor activities, but it does have two predecessor activities as activity C and D. So we draw the arrow of activity F from node 4 and ends up at node 5, which means that it would be the end of the project. The next step is to calculate expected activity completion times from the data. These expected completion times are found by using 3 time estimates: optimistic, pessimistic, and most likely in the table. Remember that these estimates are an expression of the risk associated with the time required for each activity. Once again, a short digression is helpful. Precisely what is meant by optimistic, pessimistic, and most likely. Optimistic means the least amount of time that it will require to complete. Pessimistic would be the most amount of time that it requires to complete, and most likely would be the medium or the average time that it requires to complete. Assume that all possible times for some specific activity might be represented by a statistical distribution, for example, asymmetrical distribution. The most likely time m for the activity is the mode of this distribution. In theory, the optimistic and pessimistic times are selected in the following way. The project manager or whoever is attempting to estimate A and B is asked to select A such that the actual time required by the activity will be A or greater about 99% of the time. Similarly, B is estimated such that about 99% of the time the activity will have a duration of B or less. Now, the expected time T is found by this formula where total time is equal to A plus 4m plus B optimistic plus most likely 4 most likely plus 1 pessimistic time divided by 6. Where A is optimistic, M is most likely, and B is pessimistic time. Critical path. Critical an activity or event that, if delayed, will delay project completion. Critical path would be that path on which those critical activities would be placed. The longest of the paths through the network, which means that it shows the shortest time in which the entire network can be completed. This is called the critical time of the network, and path on which it falls is the critical path. Although we will assume throughout this chapter that we always employ the as soon as possible approach to scheduling tasks, early start, there are situations where other approaches are sometimes used. One example is the simultaneous start where all resources are launching at the beginning. Another is the simultaneous finish where a facility can be moved to its next location once all the tasks are finished. Of course, delay early on in the project runs the risk of delaying the overall project if some other activities inadvertently becomes delayed. Critical path. One important reason for using as late as possible approach described below is that it delays the use of resources as much as possible, therefore optimizing the cash flow of the project, but again at some risk of delay. Float, aka slack. To find the slack for any activity, we make a backward pass, right to left, through the network just as we made a forward pass, left to right, to find the critical path and time, and the ES times and EF times for the successor activities. There is one simple convention we must adopt. When there are two or more non critical activities on a path, it is conventional to calculate the slack for each activity as if it were the only activity in the path. Thus, when finishing or finding the slack for activity I, for example, we assume that none of I's predecessors are delayed. Of course, if some activity X had 6 days of slack, and if an early activity was late, causing the event to be delayed, say 2 days, then activity X would have only 4 days of slack, having lost 2 days to that earlier delay. Gantt charts, one of the oldest but still one of the most useful methods of presenting project schedules. Information is the Gantt chart, developed around 1917 by Henry L. Gantt, a pioneer in the field of scientific management. The Gantt chart shows planned and actual progress for a number of tasks displayed as bars against a horizontal time scale. It is particularly effective and easy to read method of indicating the actual current status for each of a set of tasks compared to the planned progress for each item of the set. As a result, the Gantt chart can be helpful in expediting, sequencing, and reallocating resources among tasks, as well as in the valuable but mundane job of keeping track of how things are going. In addition, the charts usually contain a number of special symbols to designate or highlight items of special concern to the situation being charted. There are several advantages to the use of Gantt charts. First, even though they may contain a great deal of information, they are easily understood. While they do require frequent updating, as does any scheduling controlling device, they are easy to maintain as long as task requirements are not changed or major alterations of the schedules are not made. Gantt charts provide a picture of the current state of the project. Gantt charts, however, have a serious weakness. If a project is complex with a large set of activities, it may be very difficult to follow multiple activity paths through the project. Gantt charts are powerful devices for communicating to senior management, but networks are usually more helpful in the hands on task of managing the project. Another significant feature of Gantt charts is that they are as easy to construct as a network. We used the example in the previous subsection to demonstrate how to construct such a chart. An example of Gantt chart where we have the same activities as we saw in the other AOA and AON networks, the same plan, where activities A, B, C, D, E, and F are there, with activities A and B no predecessors of these activities. So, as you can see, both start at the same time, and then activity B starts or finishes early. So, activity C, which is follower of activity A, can start a bit later, but activity D and E, which have activity B as predecessor, will start a bit earlier on. Now, for activity F, activity C and D must be completed. So, even if activity D and E were completed earlier, activity F could not be started unless or until activity C had been completed, was also the predecessor of activity F. This example illustrates both the strength and weaknesses of the Gantt chart. Its major strength is that it is easy to read. All popular project management software will prepare Gantt charts, and most have some options available for customization. On balance case, ease of construction and ease of use have made the Gantt chart the most popular method for displaying a project schedule. Nonetheless, an activity on node network is still most useful for project managers to exercise control over the schedule. And the viewer may be misled if the Gantt chart is not read carefully or if it does not contain all appropriate information. The Gantt chart is similar to the project master schedule. Both are types of the bar charts and are used similarly. The major difference is that Gantt chart is intended to monitor the detailed progress of work, whereas the master schedule contains only major tasks and is oriented towards overall project management rather than precise control of the detailed aspects of the project. Summary of the chapter. Some specific points covered in the chapter were these. The scheduling aspect of project implementation was addressed. Following a description of the benefits of using a network for planning and controlling a project, the activity on arrow and activity on node approaches were described, as were Gantt chart. Scheduling is particularly important to projects because complex coordination problems. The network approach to scheduling offers a number of specific advantages of special value for projects. Critical project tasks typically constitute fewer than 10% of all project tasks. Network techniques can adopt either an activity on node or activity on arc framework without significantly altering the analysis. Networks are usually constructed from left to right, indicating activity precedence and event times as the network is constructed. Through use of the network, critical activities and events are identified. Early and late activity starts times are found, available slacks for each activity are determined, and probabilities of project completion by various times are calculated. Gantt charts, a monitoring technique, are closely related to network diagrams, but are more easily understood and provide a clearer picture of the current state of the project. However, while offering some advantages, they also have some drawbacks, such as not clearly indicating task precedence and dependencies. This is the end of the lecture. Thank you.